Uh, So maybe let's start. So I'm happy to introduce Chengyu Hu from Chongqing University of Technology, who was previously a postdoc here at NCTS, and he will be reporting on recent progress in generalized MMP.
Thank you. Thanks for the invitation. So you are also postdoc here? Okay, I was a postdoc here a while ago. A while means like 10 years. And it's been, I think, 7 years since last time I have been here, 2018. So something changed, but the most thing remains what it looks like in my memory. So it's quite missing. I wish I could stay more, but I have to leave next week. So hoping we still have time to discuss. The topic of my talk is my recent progress in generalized MMP, and I will introduce what an MMP is and what generalized MMP is, and finally what we have done in recently. And I think the talk is supposed to be the first half an hour should be like elementary introduction or something. So I will start from the very beginning to introduce what mini-model program is. Um, I still remember when I was in Taipei, I started to learn some very difficult topic like derived category or something, but finally I'm still bad at it. But regarding the mini-model program, I'm really familiar with, with this topic. So I will start. So let's suppose K to be an algebraic closed uncountable field of characteristic 0. That is C. So I don't know the other field. Of course, there are some other field, but not important. C is most important. So usually we wrote algebraic closed uncountable field. The reason is that in characteristic 0, we need the vanishing theorem. And algebraic closed, of course, this is necessary to carry out a lot of the most theory of schemes, variety, something like that. And uncountable because we usually work relatively and we need to count the fiber. So for most definition in birational geometry, countable fiber is not sufficient because a lot of definition is defined asymptotically, like relative codial dimension, something like that. You need to take the limit, and then you need the uncountable fiber. Then you can talk what the very general fiber is, which means that apart from countable closed field, a countable closed subset below over the base. So the definition is birational means that it's very common. If they are birational, it means that it is isomorphic near the geometric point. And this idea is very useful in high dimension because for curves, birational means isomorphism. But as long as you go to this dimension 2, and then you will have too many isomorphism class in one birational class, which is blow up. It can blow up infinitely times. And in high dimension, the situation can be more complicated. But for the log smooth case, we have a very good theory to describe it, which is called the Due complex. And the birational equivalence can preserve a lot of important geometric invariant. For example, genus, codal dimension, and also irregularity, on which Professor Chen is an expert. And what we want to do is to classify the algebraic varieties. And this is the starting point of mini-model theory. To do the classification, the first step is to make it the looks like a good element in the birational class. So by Nagata compactification, every variety can be embedded into a complete variety. And then you can take the blow up to make it a projective model. So we only need to consider projective variety. And by Hironaka's resolution in characteristic 0, every projective variety has a smooth model. So you can just take the resolution and suppose everything is smooth projective variety. So we need to classify these objects. And this is the basic. So for curves, this is very well known. But one interesting thing is that on curves, everything coincide and they look like very nice. For example, because on curves, birational means that isomorphism, if you only consider the smooth case. For smooth curves, if it is complete, then it is projective. So it is divided into three categories, three subsets. One is the genus is 0 and it contains only one element, which is P1. And the second is the elliptic curves. And the moduli looks like upper plane or something like that. And the general type, this is the most interesting case. So in this case, the moduli is the most interesting case because the name, you can see from the name, it's general type. It means that it contains the most elements in this set. And if you count the genus, you can divide them into these three subsets. And if you use the viewpoint from differential geometry, and then you can use the curvature. And for curvature, you can still divide them into three categories. And the third one, this is the basic idea from birational geometry, a mini-model program or something. This is the somehow looks like the degree, but in high dimension, it should be replaced like intersection number. So in dimension 1, there's no intersection number, so we only count the degree. So in dimension 1, these three notions coincide, completely coincide, but in high dimension, they are not the same, not this story. Oh, here's the classical mini-model program on surfaces. So on surfaces, it is known very long time ago, more than a century ago, by Italian school. If there is a -1 curve, which means that it is P1, and the self-intersection number is -1. And then you can always contract this curve. This is Castelnuovo theorem. And after the contraction, you will obtain a smooth projective surface. So the category is still smooth and projective. You did not run out of this category, so still remain in this category. You can continue this process. And because the Picard number is finite, and every time you contract some -1 curve, because it is exceptional, so the Picard number will strictly decrease. But here it is drops by 1. But in any case, if you contrast something, then the Picard number will definitely decrease. After finitely many steps, we will reach a model which contains no -1 curve. We usually call it minimal. This is the surface case. So for surfaces, how to classify them? The idea is to use the so-called Kodaira dimension. So usually written as the kappa y. This is the y is the minimal surface, minimal model in the minimal model sense, because in the surface theory, minimal surface maybe means some different thing. Okay. So Kodaira dimension is defined asymptotically, like I mentioned before. So absolutely, it can be defined by taking the limit, and relatively, you need to check all the fibers, so it's become more complicated. But anyway, we are consider the surfaces, so it's only defined absolutely, globally. If it is minus infinity, then very similar to the surface curve case. Y is P2 or Y is a ruled surface. Actually, these surfaces has a very, very good classification, like a projective bundle, because if you have a ruled surface, then it must be a P1 bundle. It is a theorem. I can't remember clearly, but I know this is a theorem. If you have P1 fibration, then it must be P1 line, P1 vector bundle, or something like that. So if the Kodaira dimension is 0, then today we usually call the Calabi-Yau type, which means that the canonical divisor is Q-linearly to 0 or Q-linearly trivial. But on the surface case, we still need to consider the irregularity. So by the irregularity, we can divide them into three subsets. One is called K3, which is irregularity 0, and this is the two-dimensional Calabi-Yau variety. So Calabi-Yau means irregularity So I remember the original definition of Calabi-Yau should be like irregularity equal to 0 or something. But today there are too many names with Calabi-Yau, so it depends on the situation. But this is the original one. So K3 surface is very typical, like two-dimensional Calabi-Yaus. And Enric surface, and this is irregularity 1, and the third is the abelian surface or a quotient. This is the irregularity 2, which means that it can be embedded into an abelian surface. So in this case, it has maximal Arrhenius dimension. So it has very similar to a variety which possesses a group structure and like algebraic groups. For the Kodak dimension 1, Y is an elliptic surface. And this is also very interesting, which is studied thoroughly by Kodaira. And also, this is the starting point of the later we will see. Later we will see this is called a generalized pair. So in the surface case, a generalized pair, the prototype is this one, elliptic surfaces. And for the Kodaira dimension equals to 2, and then this is the most general case. The Y is of general type, and KY is big. So since KY is definitely big, and then it is base point free by a theorem, which gives you because it is semi-ample, then it give you an ample model. And this is we usually call the canonical model. So in this situation, we reduce.
But I think in the case of
Okay, I copied this from cautious notes. So maybe he's not expert. I'm of course I'm not an expert. Professor Chen is an expert. So okay, this should be forecasted, not three classes. But in anyway, from the viewpoint of rational geometry, we can either we reduce to the curve case, which means we lower the dimension, and for the rest case, we can assume Ky is ample or maybe relatively ample or something, trivial or maybe relatively trivial, and anti-ample or maybe relatively anti-ample. This is the first case, rule surfaces. So if you forget about the lower dimension information, then this must be one of these three cases. Okay. Then we go to the high dimension, how to generalize these -1 curves and how to do this contraction as a high dimension. And speaking is always very easy, but I think the idea is not so easy. I think the original idea maybe from Mori when he was studying the Hudson conjecture, he suddenly realized one thing, which is today we call Van den Broek, and which leads to the thing we usually call extreme array. And then extreme array is the okay. -1 curve should be replaced with extreme array in high dimension. This is a very good repetition. But one thing is that if you know minimal theory very well, you will find out one thing is that extreme array is a very subtle thing. It is difficult to see. And once you go step, and then the extreme ray in the last step will immediately vanish, and the new generated extreme ray, you don't know anything information. But the only information we know is that this thing, which is obtained by Van den Broek, that is the boundedness of the intersection number. Usually we call it the length of extreme array. But one thing I like to share is that I think many people they did not know this is that later we will talk about BCHM, which is the finite generation, and we will talk about something like the existence of flips and even more like the work by me and by Hashizumi and me. And these works they rely on a positivity assumption, which means that we will work over with a very good positivity assumption. But with positivity assumption, we don't need this kind of thing. The reason is very simple. We need to bound the intersection number because we don't know how many extreme array we have. There can be infinitely many, of course, countably many. But once you have some positivity, then the number will suddenly become finite. So you don't need to bound the number because the only finitely possibility. So that's why we really don't need a band and break. So this theory, of course, it is very beautiful, but for the BC-tram setting, we don't need it. Later we will talk about what is BC-tram setting. Right? It's just something like a positivity assumption, like an ample. And then furthermore, R can be contracted. This is called the Conner contraction theorem, very similar to the surface case. Once you have some negative extreme array, and then you can contract it. And finally, you're supposed to reach a model. Either it is a contraction, which gives a modified, and this is to a contraction to lower dimension. And for the rest of the case, you will get a minimum model. So this is the minimum model program, and this is the conjecture. The conjecture is that we can go this process, and finally we reach which is called a minimal variety, which contains no negative curves. Otherwise, you will have a negative extreme array, and then you will continue this process. And the problem is that in higher dimension, there are some more complicated thing which even in dimension 3 it already occurred. So it prevents us from just running the minimum model program like on surfaces. So that's the difficulty. The difficulty is discovered by Mori is that in dimension 3 or higher, contraction will not preserve smoothness. This is the first thing. So we need some Meyer singularity, and this singularity are usually described by a sequence of number, not only one number, but a sequence of numbers which called discrepancy. And by discrepancy, you can define what the singularity, how singular it is, and then this will be preserved by minimum model program. So we just expand the category from smooth projective variety a little bit to projective variety with mild singularity. And then this is the definition of MMP. We just continue running this process. And the termination conjecture is actually even more difficult than the minimum model conjecture, because even if you have a minimum model, it depends on how you run the minimum model program to reach it. There are some easier way to reach it, for example, with scaling. But if you run minimum model program arbitrarily, then the situation will become more difficult. Okay, then let's expand in the category more. I can just see the time. Okay, which is a pair. A pair means a normal variety and a divisor with coefficient real number, such that k plus b is a Cartier. A Cartier means that it is a combination of a real combination of Cartier divisor with real coefficient. So why we need a Cartier? The reason is simple. We need intersection theory. This is what I talked previously, and even in the curve case, we need to count the intersection number, and this is the starting point of the whole program. Of course, there are some researchers like Fujino and Hashizumi. They study some pair without this assumption and make things very much more complicated. But anyway, pair is a very natural generalization of variety. The reason is simple. Why we need pair? Because we usually know not only in algebraic geometry, I think in general math, if you want to prove something big, and then maybe you only have 3 ways to do it. One is by construction, and this is the most difficult way, usually very, very rare. And the second is by contradiction, and the third is by induction. And so why pairs? Because we need to prove things by induction. In higher dimension, the information is very, very limited, and we still have very, very limited tools. So we need to reduce things back to the surface case. That's why we need the pairs. And also, this is very good. A lot of things can be reduced to surface case by adjunction. And then we can calculate the discrepancy and the coefficient and a lot of things. Okay, this is the baby example. Everything is smooth, and then you will have this one. So if it is not smooth, but with some minor singularity, for example, KRT and a plus some S, which S is also not so bad, does not destroy the singularity. And then you will still have this kind of formula. But of course here, you need to add something, some positive thing. And this is proved by Shockley, if I remember correctly. In the 1980s or maybe 1990s, I can't remember. But anyway, this is an important fact. And for this one, this is by a finite map. If you have finite map, then in this case, you have to count these ramification points, and then you will get this equation. This is also very frequently used because when you do the subadjunction, you must take a finite map. Adjunction is usually birational. Divisorial adjunction is usually birational, so there's no finite map. But for the higher codimensional ones, if you want to know the things inside the locus, and then the map is not necessarily has connective fiber. So in general, you have to take the Stein factorization and with the fibration and a finite map. So finite map also frequently appear in the induction. And here's another example is the canonical model formula for elliptic surface. And we will discuss later because this is the prototype of the so-called generalized pair. Okay. For the MMP, we already know that a class of minor singularity, for example, KRT, and the more general one is LC. The difference between them is that KRT is like the discrepancy to be strictly positive, and LC is non-negative, like a boundary. So it is very natural to think about if log canonical thing is the boundary of KRT in the moduli space, but actually it is not sufficient. The correct one is SLC, semi-log canonical. But anyway, log canonical itself is still very interesting because it behaves very different from the KRT. And this theorem is proved by many mathematicians. For Q factorial KRT pair, we can run minimal model program. Q factorial means that every Weyl divisor is Q Cartier. This is also a condition, a singularity condition, a very strong singularity condition, which allows us to apply intersection theory freely on this variety. Of course, the termination is not known. In higher dimension, it is most conjectures are widely open. We only know very small thing, but usually we call this one thing general type. This is proved by Becker, Cassini, Haken, and McKernan, a very famous paper called BC-Trem. And they proved a special case. And this sentence is I added. This is in my opinion. This is the first step in high dimensional termination. Why I call this is the first step? Because later when we try to do something, for example, we want to expand the category to not so mild singularity, for example, from KLT to LC, or even more general. And the one thing is that we cannot give an independent proof. Our proof is finally reduced back to KLT case, and it depends on BC-Trem. So that's why I call it the first step, starting point. You cannot avoid it. You cannot give an independent proof to prove some stronger result. Seems almost impossible. On every strong result, what we do is to reduce back to the KRT case. So I believe this is the first step. Cannot avoid. So the condition is like this, and of course this condition is slightly different from the original literature, but I think this is easier to describe. Also, this condition is used in Karl Mata's book. In Kawamata's book, he also used this condition, which is that B, the boundary, contains an ample divisor. Then we provide a very strong positivity to the boundary. Of course, in the original literature, they consider the case that the K itself is big, but this situation is the same because K itself is big. You can make K into 1 minus epsilon K plus epsilon K, and then you can make epsilon K into a boundary which possessing this property. So actually, it is the same thing. So the result is very standard. Either we have a good minimum model or we have a modifiable space. And this is, I think this is the very standard formulation of the minimum model theory today, because these two class, once we get these two, by Cauchy-Pierre's philosophy, we almost get the termination of MMP with scaling, but of course not arbitrary MMP, but MMP with scaling we know. Once you have this, you have a minimum model, and then you will have an MMP with scaling. So this is the BC-CHAM, and also Xu gives an analytic proof, and Lazic gives a purely algebraic proof, and this is a very beautiful viewpoint. Somehow Lazic shows that this theorem, BC-CHAM, and its related results, does not rely on classical MMP, because Lazic's proof is completely algebraic. He does not rely on the Morris theory. So that's what I talked before. The reason is simple, because here you have some ample condition, which means that in each step, the extreme array is finitely many. So you actually don't need something like banana break or something. Everything is finite. Okay, and this is what we do later, how to generalize the BC-CHAM result. In Becker-Hu, we proved a special case, and in Hu 17, I proved this. And then later, Hashizumi simplified this inductive argument, and then we obtained this result. Just like I said before, the proof of this result is to reduce back to BC-CHAM. So it is not independent proof. And I strongly suspect that there will be an independent proof. So my feeling is that we can only reduce back to the BC-CHAM, and I will talk my reason later. So the condition is exactly the same thing. The only difference is that we just changed KRT to LC. Of course, you can replace projective to relatively projective, but that's the same thing. For pairs, relative and absolute are almost the same thing. But for G pair, it is kind of different. And then if it is Q-Cartier, then it is finitely generated. So it's nothing. It's just a very easy corollary. And the third corollary is this corollary is kind of interesting. It appears in Hashizumi Hu. That is in BC-CHAM, we know a KRT phenotype. And then if we have a morphism, then its image of this morphism must be KRT phenotype. So we would like to ask if this hold in the LC category. And this is what we proved. The proof is that if the right is Q factorial, then it's okay. And if the image is Q factorial, and then it's also okay. But if both of them are not Q factorial, we really don't know how to prove it. The reason is kind of subtle, but we really don't know how to do it. And even now, we don't have any idea to go beyond this result. And this theorem is also the same thing. MMP with scaling terminates, just like I mentioned before. As long as you have minimum model then, or modifiable space, then any minimum model program will terminate. With scaling will terminate. But here it's different. Here is different. Here we can run a minimum model program on K plus B with scaling, which terminates not any MMP, just there exists an MMP. There exists an MMP. And this is proved in Hashizumi-Hu. The reason is kind of tricky. Why we cannot run any MMP? Because in BCTRM, why any MMP terminates? The reason is the finiteness of minimum model. So you can, with scaling is something like there is a segment and then you go this direction to 0, and after finitely many steps you will reach 0, and then this will be the minimum model. And you know there are only finitely possibility you can choose. So every time you just go down and finally you reach it. So the only thing you need to prove is that on each point of the segment, you cannot have infinitely many process. This is the only one you need to prove, because you only have finitely many points, they will stay. So the only thing you want to prove is that you cannot stay at one point infinitely many steps. In BCTRM, this is very easy by the finiteness of minimum model. You can only have finitely many minimum models, and the flips will change the minimum model. You cannot go to the same minimum model twice, and then you run out of, you run over all the minimum model. You have to go down to the next point. So after finitely many steps, you will terminate. But in the LC case, the situation is different. So we cannot expect something happen for very subtle reason. But this situation can be avoided in the in this case Q factorial. But if X is Q factorial, and then we still have finiteness of minimum model, so you can any MMP with scaling will terminate. This is proved in Hu 17, and this is not in literature. We just discussed very recently. The reason is that why I can prove this is that a stronger result is this. If this project Q factorial LC pair, and then finiteness of minimum model still correct, we can prove it. And if we remove the Q factorial assumption, Hashizumi gave a counter example that it can happen that I think today Hashizumi called this category the polarized LC pair. Polarized means we have some ample divisor here. For polarized LC pair, it can have that. It could happen that it has infinitely many minimum model, and the example is given by Hashizumi very recently in our private discussion. So, which means that if we want to prove any MMP with scaling terminate, seems almost quite impossible. A very difficult question. Okay, let's go to the generalized pair part. And for the generalized pair, the starting point is like this. The starting point is called polarized pair. Of course, this is not a good name because polarized is used too many times in different content. But anyway, in the beginning, we call it a polarized pair because we add a nav divisor to the boundary. Of course, if this is ample, then it should be something like polarized, but it's just nav. Why we need to consider this kind of thing? Because we want to show that Nakayama Zariski decomposition, which is the higher dimensional analog of Zariski decomposition on surfaces. We want to show that birationally NZ decomposition is somehow equivalent to the existence of minimum model. So in this case, we need to consider, for example, if we have some decomposition like this, and then we just add something to the boundary to make it like a polarized pair. And another reason is like this: from the elliptic surfaces, the Ks here I should be written like Q linearly equivalent, not equal. Q linearly equivalent to the pullback of Kc plus Bc plus Mc. And Bc is the discriminant part, which is calculated by the log canonical threshold, and MC is called the moduli part. In the surface case, it makes sense because it somehow measures the moduli of something. And by Kodaly's theorem, we know that the MC the denominator is always divided by 12. So 12 MC is integral. This is the example of the elliptic surfaces. And in high dimensional, we also expect this kind of thing happen. It's called canonical bundle formula. And it is proved also very, very long time ago by Kawamata, Ambrose, Fujino, and many mathematicians. And of course, the formulation is also very similar to this one. Okay, here we go to the Becker Zhangdeci on 16, the definition of generalized pair. So you can compare with the definition of generalized pair and the polarized pair here. The only difference is here we require M to be NF, and here we require M to be BNF. BNF, I will explain a little bit what is a B divisor. A B divisor is something like you consider all the variational model and you consider the divisor, weight divisor on each model. Now, of course, in resolution, they are Cartier thing. And they preserved preserved by push down. And BNF means that on some model, it is NF, and in higher model, it is the pullback of this NF divisor. This why we need this? There are two reasons. Also two reasons. One reason is that these objects, they are not invariant on the MMP. Once you run a minimum model program, and then you will immediately lose the nefness of M. So you can expect M to be nef when you run minimum model program. So one thing is to make it be nef. So on some variational model, it is nef, but it is simply the push down of this nef divisor. So then this can be preserved by minimum model program. Then, of course, from this viewpoint, we just expand the category, which allows us to run minimum model program. So that's the very basic idea of minimum model program. We just expanding the minimum model program. Expanding the category, and then we can run minimum model program, and which allows us to use more tools to do more inductions. And another viewpoint is that by canonical bundle formula. Okay. Now, canonical bundle formula for generalized pair, we only consider one situation, which is called the Calabi-Yau fibration. Now, the Calabi-Yau fibration, maybe I can use a chopstick. Okay. So for the Calabi-Yau fibration, is something like that. Suppose we have a pair here, maybe and then K plus B is Q linearly or K linearly, R linearly 0 relatively over Y. This is called the Calabi-Yau type. And there's another thing which is also very interesting is that Ambrose usually call this parabolic fibration, which is like this. So the relative codal dimension is 0. Of course, this assumption is much stronger, and this assumption is weaker. But for the generalized pair, we usually consider the former because we really don't know how to deal with the second one. Until now, we really don't know. Because the reason is because the starting point is by Philippe Pazzi. His idea is that if you have a generalized, this is a pair. If you have a generalized pair relatively trivial, k relatively trivial over y, but here, here I made a mistake. This should be q pair, GRC q pair, which means that the boundary must be q, and m is also q for rational with rational coefficient. And then on y, you will get a very similar thing like the canonical bundle formula. You have ky plus by plus my, which is by is calculated in the same way by log-canonical threshold, and my is supposed to be BNF. So by Philippe Pazzi's idea that maybe this is also Cauchy-Becker's original idea, that Calabi-Yau fibration, the generalized pair, can be preserved under the Calabi-Yau fibration. So it allows us to do one more direction for induction. One induction is by divisory adjunction, and now we have, as long as you have a fibration which is Calabi-Yau type, then you will still have something like the induction way. If you suppose something which is good on the base variety, and then you can lift to the the whole variety. Here, NQC first appeared in Han Jinjun and Li Zhai's paper. It means that it is a convex combination of NAF-Q device. So I'll explain why it, for the technical reason, I will discuss later, but first I will talk about why it appears that we have the NQC condition. Because one thing we know is that K plus B, if it is Q linearly to 0 over Y, and then it must be Q linearly to the pullback of some Ky plus By plus My. Here, this is Q divisor, and everything here is Q divisor. So the idea is that if it is R divisor, and then we can take a convex combination to make it inside this a very small polytope. For example, if we write B as a sum of alpha I Bi, and then we still have, for each Bi, we still have this kind of thing, the pullback of Ky plus Byi. And the thing is that My will still the same. It does not depend on Bi. When you perturb the coefficient of Bi, it will only affect the coefficient of Byi. So here, you just combine them together, and then you will get something. Okay, this also change. Ky plus something like alpha I Byi plus alpha I My. Okay, this is what we usually call the NQC. It means that it is a combination, a convex combination of NAF-Cartier divisor. Closed adjunction is that what Filipazzi proved is that if you have XB plus M here, this is generalized LC, and if relatively trivial, and then this will be the pullback of some generalized pair. And also the singularity is preserved. If this is GKLT, and then this is GKLT. If this is GRC, then this is GRC. So that's why we call this preserved. In fact, Kocher-Becker, he proved a stronger result under some situation. If this is something like epsilon LC, and then this will be delta LC, and delta depends on epsilon, something like that. This is the adjunction for fiber surface. And the name is from Ambrose paper. Maybe you don't need to use, if you don't like it, this terminology, you can just forget about it. It's just a name. So in Ambrose paper, he called it adjunction for fiber surface space. But if you don't like it, you can just forget about it. It's just something how to relate the fibration, how to relate the whole variety and the base variety. Sub-adjunction, okay. This is proved by Han Jingjun and Liu Wenfei. And the sub-adjunction is like this. Suppose we have some, okay, GLC. Even for the LC case, sub-adjunction is very important. I remember for the log canonical case, it is proved by Kawamata. and which is called the subadjunction. The idea is like this. Suppose you have an S, which is a center, RC center of this structure, and then since it is an RC center, then you can take the resolution of this one. And here, S prime will be a divisor. And here, S is higher codimensional. So they are not of the same dimension. So this map will be decomposed into two by the Stein factorization. Okay, let's what should I anyway. So of course on S prime, you by adjunction you will have something like Ks prime plus Bs prime plus Ms prime, which is the restriction. And then you need to push it down because this one is obviously relatively 0 over S. And then you can apply the canonical boundary formula to T. And then this is a finite map. And then you need to apply the canonical boundary formula for the finite map again. And then you will reach, you will get a generalized pair structure here. So this is the idea. So here, this part is kind of easy. The subtle part is here. The subtle part here, why it is subtle pair? Because you need to show that this kind of thing is relatively 0 over S. But this is not so obvious. You need to do something. But anyway, it's not difficult. Just calculate by, because everything is calculated by log-Hancock ratio. You just need to calculate very carefully on the variational models. They are not difficult, but just complicated. The RC center, yes. So without the generalized pair, and this is proved by Kawamata. Kawamata proved that K plus B restrict to some S will be something like Ks plus Bs plus something. But here we know the plus something should be the modular part. So in Kawamata's original paper, maybe he used some ample divisor to perturb the thing and to make it into a pair. But in fact, it should be a generalized pair, not a pair. The reason is that it is obtained by canonical boundary formula. So even in the pair case, the subadjunction will give you a generalized pair. But in Kawamata setting, it's kind of special. So because he only considered the minimal RC center, so that's different. But for the generalized pair, for arbitrary RC center, you can apply the canonical boundary formula and apply canonical boundary formula for finite map. Then you will get the restriction of the generalized pair here. Here should be naturally will have some structure like this, such that K plus B plus MS, which is K plus B plus as a divisor which restrict to S. So we will get this formula. And this is called the subadjunction formula. And then this formula can be obtained by the canonical boundary formula. And this is the whole idea. No, positive. Always possible because Kawamata only considered the minimal RC center. So minimal RC center is kind of generalized KRT. So you can add some very small ample divisor to perturb the coefficient to make the NEF divisor become effective. Because you can imagine an effective divisor plus some ample will always be ample. And then you can find something added into it. But for the generalized pair case, the situation will be more complicated because you already have some, if it is not minimal, then you already have some RC center. Then maybe you cannot perturb the coefficient on this boundary. So So Karl-Martha's idea only applied to minimal acid center, but if you allow the category to generalize pair, then subadjunction is okay. So the third one is using the idea from the second one, and which is also used in my paper. And what we do is that also we only consider NQC. NQC is very subtle and important assumption, which will make things much easier and much closer to the classical pair. So NQC G pair is actually very similar to pair, and because you add, of course you add some NAF divisor, but this NAF divisor can be reviewed as a Q divisor, NAF-Q divisor. And I will explain later that the NAF-Q divisor is very different from the NAF-R divisor. So for the generalized pair, if you have very strong assumption, positivity assumption, and then NQC will go to the, we're very similar to the things like usual pair. What happened? Someone talking? Is this talking related to talk or not? Okay. I cannot use the, how to, cannot control it. Yes, what happened? Still cannot. What happened? Still cannot control it. Maybe I just use the laptop. Huh? How to go to the last page? Okay. Okay, it's working now. And this is proved by me. And if we have a log canonical pair on the top, and on the base variety, we will have a GRC pair with log abundant data. And log abundant is very similar. Is kind of looks like good assumption, but still, it is far from the semi-emptiness conjecture. To be honest, I don't know why Shortcroft proposed this conjecture. Shortcroft proposed the conjecture is like that. M is B semi-ample. He expected M not only NAF, but semi-ample. I don't know why, because I cannot find any clue to this conjecture. I don't know the reason. Maybe I need to ask himself. But anyway, what I can prove is that it is log abundant. And also by Zhihao Liu and Xiling Yao, they combine my result and Felipe's result, and also Felipe's result is only for Q data, and they for NQC data, but they're actually the same. For NQC and Q, almost the same thing. And the GRC pair with log abundant data is closed on the adjunction for Calabi-Yau fibration. So on the top, you have GRC pair with log abundant, and then in the lower, on the base, you have the same thing. And this is the theorem by Chenhai Liu Xie with non-NQC data. It also works, but the information they cannot get an abundance information. But I think it is not difficult. And this is not difficult. So anyway, for the Calabi-Yau fibration, as long as you have GRC pair, and then on the below you will always have GRC pair. I think this is not difficult problem. It is not difficult, but very complicated. You have to calculate very carefully, and that's the only problem. So, but for the rest, I don't think that it will cause much difficulty, because because the canonical boundary formula, you just reduce everything back to Ambro or Fujino's original setting. Maybe their setting is from Kawamata setting, so which is from the variation of Hodge structure. So as long as you have this structure, then you will have the rest. So the rest is based on the very original one by MMP. So so once but the original one you cannot prove by MMP. You can only prove it by some other thing. One idea is to use the variation of Hodge structure. Chen Han, Liu Xie used a different approach, which is by Ambro and some other guy. I can't remember the name, but this approach is from Ambro and some other guy. Maybe the abbreviation of that paper is ACSS. I remember Liu mentioned this to me, but I cannot remember. They use, but this paper is different. They use different approach. But anyway, you can still use you can still use the classical approach to obtain this one. So I don't think it will be very difficult.
Sorry, question about the previous statements. So with this log abundant data, so generalized pair with log abundant data is a particular case of a generalized pair, or the other way around?
A particular case.
This is a pair, so it's like a
yes.
generalized pair with extra data.
Yeah, with extra, very strong assumption. Log abundant data is quite strong assumption.
Okay, thanks.
But since we consider about we will only consider about the situation like we have some ample devices, then maybe this are even weaker than that. So later we will consider even stronger assumption. Well, without this assumption, we really don't know how to do it. This is what I mentioned before. So everything we can do is based on BCHM. So what we can do is just to from KLT to LC, LC to generalized LC, but we cannot remove the positivity assumption. Not only remove, we cannot even weaken this assumption. And this is the point. So BCHM is still, I don't know how to describe this. It sounds somehow like a mountain. You cannot go beyond it. You can just rely on this, and then you cannot go beyond it. I don't know how to go beyond this. It was written like 20 years ago, and 20 years has already passed, but no one can really. Maybe Haken, the Mayan Haken Pong, they proposed something which is looks like a little bit beyond, but still not solved completely. I remember a postdoc of Professor Chen, a former postdoc, he is doing related topic, Mario, and still not completely solved. Even if it is solved, I still think it's difficult to completely go beyond the BCHM. So without the BCHM, we don't know how to do it. The reason is very simple. Because in BCHM, this ample divisor plays, it plays the role to provide the vanishing theorem. So you can think like this: the whole BCHM is based on the vanishing of H1. You only need a H1. You don't need something else. You only need H1, and then you apply the long exact sequence, and you will get the surjective of H0. And then you can lift the section, and then this is the whole idea. Otherwise, if you don't have section, you cannot play with any tools. So the whole idea is that you need the vanishing of H1, or at least the injectivity of H1, and then you will have the subjectivity of H0. But so for the rest of the case, I really don't know how to do. Here, abundance for G pair fails in general, even in NQC case, even in the Q divisor case. This is also the toy, the wavy example, the toy example. It's quite trivial, so I don't want to mention this. The interesting thing is this one. This one is not numerically semi-ample, which means that K plus 3 E prime, it is not semi-ample itself, and any divisor in its numerical class, it is also not semi-ample. This is kind of different because usually minimal model program is something like a numerical process. We only consider the intersection number. So for generalized pair and usual pair, we will ask something like, if we only consider the intersection number or in the numerical class, are they the same thing? And And this counterexample shows that they are not the same thing, and they're different. Okay, this is the abundance of generalized pair with joint with Kochev-Vilka. And actually, I know very, very little thing about the, sorry, Heikam Kananshi, but I wrote it in the Chinese character, so it does not appear. I wrote it because the PPT does not show the Chinese character. So it's Heikam Kananshi Tenyang. And their result is like this. Given dimension, given volume, and given some DCT set, which is the coefficient. Why we need a DCT set? The reason is traced back to Shaklov, because when you apply the divisory adjunction, the coefficient will satisfy DCC, even if you from the finite set of coefficient, and in lower dimension you will have a DCC set. You don't expect this to be finite, but anyway, if you start from a DCC set of coefficient, and in the lower dimension you still have this DCC. So DCC set is a very good inductive assumption. So every assumption here is like inductive. You can apply induction to lower dimension and then prove everything. And this abundance conjecture for generalized pair is proposed by Kochev-Vilka, and they also show this is false. Back at 21, they proved that this is true for KRT, but false for GRC. That's very surprising because he told me that he strongly expected this to be true, but finally they found a counterexample, which also means that the generalized pair, even in the Q case, it does not behave very similar to the usual pair. And then he proposed this weak abundance conjecture. But anyway, what we want to do is what we have done is to generalize this one by Heikam Kananshi Chen-Yang. Once we want to do some boundedness theorem, the natural idea is to consider the family. Of course, the smooth family is the most simple case, and this is proved by Heikam Kananshi. And their result is like this. Suppose we have a relatively log smooth family. Suppose they are all LC. And if at some point on some fiber, it is good, K plus delta is good, K0 plus delta 0 plus, it is good, which means that relatively on the whole, it is good. It has a good mean model. And on each fiber, it is good. So their result is quite strong, which means that if you have a good fiber, which means that the rest fiber are all very good, as good as this one. And also, the relative case, you can run MMP, which terminates. Their proof is not purely algebraic. They rely on some analytic result by Benderson-Pong. And the original idea of Benderson-Pong should trace back to Shang-Ying invariance progenera. And of course, in Xu's original context, he did not consider the boundary. And in Benderson-Pong, they added the boundary. But I think the basically idea is the same. It's just to calculate the progenera and extend the section, and you will get this. And this cannot be done by algebraic way. So this approach is just totally forget by us. So we don't use this approach, because for generalized pair we cannot expect something like this. In general, we even cannot expect the inverse progenera or something. I did not show example here, but it was shown in Birka and Haken's paper. A very, very trivial example shows that you cannot expect at least you cannot expect trivially something like inverse progenera or something, but maybe you need to add some assumption, or maybe you need to change the formulation or something. I don't know, but at least from the purely algebraic viewpoint, we use a completely different approach. The approach is here, where we call generic MMP. And generic MMP means that in many fibers, they are not even generalized fiber. So the setting is like this. Suppose we have a triple here. So XP itself is just relatively log smooth and nothing strange. The strange thing is we add some defines here M. M is not necessarily NEF, but some fiber it is NEF. Not on every fiber it is NEF, but on some fiber it is NEF. This is kind of different because NEFness is not an open condition. So if you have one fiber which is NEF, you cannot expect a general fiber around this fiber is NEF. It is not open assumption, not like ample. For ample, if one fiber is ample, then you can expect there is a neighborhood on the base variety, and over this neighborhood, every fiber is ample. But for NEFness, it is not true. You can find a counterexample on Lazarsfeld book very easily. It is not true, even for Q divisor. But of course, here we only would consider the R divisor because it does not cause too much difficulty. But in this case, how we run MMP, the idea is like this. Here, this is proposed by Kocher-Becker. Suppose we have a subset C prime, and on this C prime, we assume M is NEF on this subset, which means that if we pick an ample divisor A, and we sufficiently small number epsilon, here I use fractional, maybe they not use not necessarily, just small number epsilon, and then we can find an open subset of this is the open neighborhood. I used the wrong number. The open neighborhood of Z prime. It is open subset of Z, such that M plus epsilon is ample over this neighborhood, because ample is an open condition. So you can always find a neighborhood which is ample. And then by BC-Tram, we can run minimal model program over U epsilon with scaling of A. And then we decrease this epsilon, and the epsilon can be chosen arbitrarily small. And of course, at the same time, we need to shrink in this open neighborhood, U epsilon. So the U epsilon is become, when we run MMP, we not run on some fixed variety over some fixed neighborhood, but each step we change the neighborhood and we change the inverse image of the neighborhood. So, but anyway, this neighborhood will contain all the fibers of Z prime. So this is our result. We can run minimal model program like this, and after finitely many steps, we will reach a model on which we don't know what happened outside the Z prime, but at least we know inside the Z prime, and they are NEF. This is we call it the uniform termination, which means that no matter how many points are in Z prime, as long as they have minimal model, then you can run minimal model program, which terminates uniformly on this fiber, which means that they can achieve their minimal model almost in bounded steps of the same bonds. So you can imagine like this. For each X, S, BS prime MS, they have minimal model, and we run MMP, it will terminate. But I don't know how many steps I will reach this minimal model. But here it shows that if they belong to some bounded family, you can run minimal model uniformly, and they can reach their minimal model at the same steps. So they have the bounded steps like that. The idea is like this. Now, of course, for the relative setting, if you run minimal model program, it does not occur on every fiber. So it could happen that on some fiber, in this step, it is still isomorphism or something. But anyway, the whole steps are bounded or something like that. So that's why we call it the uniform termination. And the manuscript is written quite a long time ago, like even more than half a year, and it will appear on arXiv soon. So the idea of the proof is, I will not explain too much detail, but the idea is quite simple. The only difficulty is the step two. Step two is the difficulty. So the step one is actually somehow like special termination, which means that you run MMP, and then after finitely many steps, you will reach some model which is already NEF on this special fiber. This is not surprising because this is very similar to special termination. And the second one is quite difficult. Not quite difficult, but it contains some new idea. We need to show it not only terminates near the fiber, it also terminates on the whole neighborhood. Of course, the neighborhood does not mean every fiber. We only consider those fibers in Z prime. And the step 3 is that because Z prime is quasi-compact, then you just glue them together, glue this neighborhood together. And this step is quite easy. So the idea is like this. Okay, and the last part of the talk, I will discuss some my recent works on non-NQC GPairs and on some how to run in the MMP on non-NQC GPairs. And there are some way which is interesting to look at this. One is that when we generalize the Calabi-Yau type fibration or Calabi-Yau type variety, which is minus k plus b, is NEF. This is like a generalized Calabi-Yau type, but not Calabi-Yau type. Minus k plus b is NEF. Also, you can view this as some weak funnel or something. But anyway, this is one motivation. And another motivation is from recently, Haken, Dust, and other people, they are interested in killer MMP. And in killer MMP, what they do is not, they are not running MMP on killer manifold. They are running MMP on projective manifold, but with some killer class. That's their point. I don't know the detail, but I guess it will be very difficult to directly running on killer manifold, but it is still interesting enough to run MMP on projective manifold with some killer class. But killer class is usually to be NEF and even more general than our setting. So anyway, this is the P sigma is the positive part of the Nakayama-Zariski decomposition. So for every divisor, you have a Nakayama-Zariski decomposition, which is P sigma part and N sigma part. Here it means that it is birational, not on X itself. It is birationally part. So the idea is quite simple. If you have a mini model, which is birational, and then you take common resolution. On this common resolution, the pullback of this guy will be a pullback of this guy plus some exceptional divisor. And the exceptional divisor will be the negative part, and the pullback of this NEF part will be the P sigma part. If you have mini model, then you will definitely have this one. But what we are interested is in the converse direction. If we have some NZ decomposition or related thing, do we have mini model? And this is very frequently used. And when for usual pair, it is established by Birka and me. And the main technique is to run MMP, which is P trivial. Here, P means the P sigma. So what we do is to run MMP with some in each step, the intersection number with P is trivial, is 0. Okay, so the same technique works. If M or P is NQC, that's very easy. But for the general case, it will be more difficult. For the NQC case, it is written in T, I forgot the name, Tascan, I cannot remember. She is Xilin Yao in their joint paper. But actually, they're actually the same with Birka Hu. If it is NQC, it will not cause any difficulty, almost the same thing. But if it is not NQC, it is a NEF divisor, and then the thing will be very different. Okay, I will explain a little bit why the situation is very different. So the idea is like this. if we have a NAF divisor, which is NQC, so these PI are NAF-Q divisor. So we can, for any curve, the intersection number will be like this. So for each PI, the intersection number with C will be something like a rational number. L can, so this one will be something like this: alpha I, Mi, Li. So you can see from this equation, if it is not zero, if it is positive, then it is must bounded away from zero. It cannot go to, because this Mi will and alpha I will give you the minimum. If you if it is positive, and then it will be it will be bounded away from zero, and also the intersection number will be discrete. You cannot have dense intersection number. You cannot have dense intersection number. But here the example shows that for NAF-R divisor, you can have NAF, you can have dense. So the intersection number is dense in R. You can always find some curve, and which in particular you can always the set will is not bounded away from zero. So in this case, K plus P is not numerically non-vanishing, because in minimal model theory, a very important conjecture is the non-vanishing conjecture. So we would like to ask if G pair, we can also expect non-vanishing conjecture. For NQC G pair, it is expected. There is a conjecture which predicts that all NQC G pair should have at least in the numerical sense, in the numerical equivalence, should have some non-vanishing. But for non-NQC, it is wrong. So very recently, I told some people, I think just my own feeling, I think it could happen that the non-NQC G pair minimal model theory does not really work. I even doubt some pair if they have minimal model or not. But of course, they oppose to me. They say this is impossible. Any pair like G pair, they must have some minimal model. I don't see any clue. The reason is that it's very subtle actually. If it is non-NQC, and then you cannot control the intersection number. So here are some way we still can run, which is we call it the P-trivial MMP. This is proved very recently. I think I will propose I will put it on arXiv maybe in this weekend. It was written a couple of months ago, and I already circulated to some people like Kocher and Zhihao Liu and other people, and it remains me to do is the introduction. I still did not write the introduction part, because usually the introduction part is the most annoying part. So I just leave it to the last thing I do. But yeah, that's also Liu Zhihao suggested. He said he always used ChatGPT, never wrote by himself. So I told him maybe you can write it and I just copy from your paper. But anyway, the main theorem is already written down, and the proofs. Here, actually, the second part is more important. If this means the fractional part, which means not the integral part, with some fractional coefficient. Even you can think with irrational coefficient, it should be sufficient, not only rational. You can even forget about the rational part. And then you can run MMP with on K plus B plus M plus AP As long as A is sufficiently large, then it will be P-trivial, which means that the intersection number of P with any extreme array is bounded away from 0. You have some lower bounds, and then in this case, you can find this alpha. So in this situation, we can do, but this situation is strong, not so easy. And here the theorem, what we can do is that suppose now the numerical non-vanishing. Here I suppose the numerical non-vanishing, because for non-QCG pair, it is not expected. I already have some counterexample. So this assumption is very strong for non-QCG pair. This assumption is trivial for NQCG pair, but strong for non-NQCG pair. This is a subtle thing. But in this case, if it is KRT singularity, and then we have this conjecture. And we are interested in what if it is holds for GRC pair. But for low canonical pair, it requires a much more complicated technique. As I spent a lot of pages to work out it, and then finally I can only prove the lower dimension. Unlike GKRT, KRT I can prove arbitrary dimension, but for the LC case, even if I assume non-vanishing, I still can work out the dimension 3. And also here, if M is log abundant and it's dimension 4, but anyway, it's not so important. This one is more interesting. The non-vanishing plus NZ decomposition, we will have this one. And the more interesting thing is that the technique I developed to solve this problem is this special termination. Let's forget about the technical definition of P-trivial MMP, because this is too technical. But anyway, the idea is quite simple. The idea is just to run MMP with scaling, but in each step, the intersection number of the extreme array with P is 0, so P will be preserved to the next, and you will preserve P during this process. So the idea is very easy. And the interesting part is this one. This is the interesting part. As long as you have a decomposition like this, here I don't require N to be effective. So in fact, I don't require this to be some Zariski decomposition or not. As long as that you can write this as an F divisor plus some effective divisor, not effective divisor, a Q divisor. Here the most important thing is Q. N is a Q divisor, and then we can run MMP if it is P-trivial, and then it has a special term. We will have something like special termination, which means that you can have a lower dimensional sequence of MMP. Of course, I simplified a lot of things. The original statement is more complicated, but anyway, the philosophy is the same. The philosophy is like this: we have NAF device here, and in each step, P is trivial, and we have Q device here, and in each, and then we will have this sequence which is good. Why it is good? I will explain to you my philosophy. The philosophy is like this. Why now NQCG pair usually very difficult? Because we cannot control the coefficient of this guy M. We cannot control the intersection number of M with the curve. So the intersection number of M with C, it is difficult. It can be dense. We must make it discrete. Otherwise, we cannot apply any good minimodal theory. But how to make it decrease? You can look at the right-hand side. N is Q, so that the intersection number will be discrete by 1 m's. And the P is trivial, so in each step it will be trivial. So on the right-hand side, the intersection number is discrete. On the left-hand side, K plus B, we all know the intersection number is discrete and bounded from below. So the intersection number of M will be controlled. So this is the idea. So this is I think this is even more interesting than the main theorem. I mean, that is only the byproduct, and I think this can be used in some other places. Okay, I think I'll stop here. Thank you.
Yeah, thank you very much for a nice talk. And is there any questions?
Sorry. Yes, yes. What's the reason? Because the reason is that the inductive assumption cannot be preserved. So, for example, we have NZ decomposition, but this decomposition cannot be preserved in lower dimension. In lower dimension, you only have something decomposition, but which is not the NZ decomposition. So in this case, you cannot directly use the induction theory to apply the induction theory to get this. But in dimension 3, because we all know any minimal model program for surface is good. So if you can pass it down to lower dimension, then everything is good. And in dimension 4, it's the same reason here, because you can always we can always reduce the three-dimensional case to the usual pair and apply Morris results. And the idea is that I think that this is not a good question. This is the problem. I think NZ decomposition does not really make sense for non-NQC pair. So I think that this is the problem. So I think this theorem will be more interesting, which allows us to do some induction. But NZ decomposition, the question itself does not have a good inductive assumption. So the idea is to use this to apply this theorem to some other related question, which has much better inductive assumption. For example, recently I joint work with Zhihao, the existence of GRC flips. I think this can apply this. Well, I will explain why this can explain, because for the existence of GRC flips, the setting is like K plus B plus M plus A, which is relatively trivial. And then you can put P as the trivial device, and then you can put A to be minus N, because N is not necessarily effective, so everything is good. So you can apply this to the GRC flips, apply this to some other structure, but for the NZ decomposition, I think it's a not good application of this theorem actually, because the inductive assumption fails in lower dimension. But anyway, without this, you cannot even work out the three-dimensional case, because you even don't know how to do it. At least this allows us to go to the surface case.
So any more questions? So maybe about this thing you said with the boundedness. So there was this boundedness result for generalized KLT, Calabi-Yau pairs, right? And that failed for, not Calabi-Yau, just
Yeah, feels, but I'm.
Yeah, in the beginning you said that you can think somehow of LC or semi-log canonical as the limit of KLT, but so here you cannot think of generalized LC as the limit of generalized KLT.
Yeah, that's the
Why
problem.
not?
I don't know the reason, because Kasia Becker, he proposed this thing to me, so I really don't know the detail, but he just told me that seems it's not working, so we have to consider something like this one, this weak boundedness conjecture. So, but the idea is that we still need to work out the Heckman connection. So that's what I did. What I did is just MMP. I really don't know the detail of this boundedness. Maybe this year I spend more time to read this part.
So, somehow people working on this, they don't see this result as some kind of maybe reason to think that these generalized pairs are the wrong thing to consider. They still think generalized pairs are the right thing to consider, but somehow this doesn't work. Or
The
what?
generalized pair, it is a generalization of pair, but this notion is not the unique candidates. It has some other candidates. It depends on your philosophy, which one you would like to choose. And the generalized pair, because Kasia Becker likes it.
Okay.
That's the reason. And also he used it to prove BAB, and so some people, they have confidence in it. But the point is that the more we do this, in fact, I feel we need to add some extra assumption. So I doubt only Neff may not be a very reasonable condition. But of course, what we are interested in is we add some ample device, and then everything becomes reasonable. But apart from that, that's different story. But for the generalized pair, I think even Carter Becker himself, he did a very little thing because he's mainly interested in final case. But in final case, in most cases, you can add some ample device. So just change the generalized pair to some much easier setting. I don't know for the most general case if generalized pair is. I really don't know. There are some other candidates like Ambro or Fujino's, what is that name? Quasi-log scheme or something. But anyway, they are all from the canonical bundle formula. So I think the philosophy is the same. We need to apply induction from canonical bundle formula. So we need to use some structure which is preserved on the canonical bundle formula. GPair is only one candidate. There are some other structure which is also preserved. But I know very even less than this one.
I see, thanks.
And then mainly I'm interested is add a very strong assumption, not only generalized pair. Only generalized pair, I really don't know how to do it.
Any more questions? Okay, so if no more questions, then let's thank the speaker again. Thank you.